All right, let's dive into the physics of light. We're going to unpack the surprisingly simple formulas that control everything from that weird reflection you see in a spoon to the giant lenses in a space telescope. You've totally done this, right? You look into a funhouse mirror, or even just the back of a spoon, and suddenly your reflection is stretched, shrunk, or totally flipped. Well, that's not magic. It's math. And that's what we're here to do. We're going to build the exact toolkit of formulas that physicists use to figure all this stuff out. By the end, you'll be able to see the world just like they do. So let's get into it. Okay, first things first. It all, and I mean all of it, starts with the physical shape of the mirror or the lens. That curve is what tells the light what to do. So before we can even think about formulas, we need to get one key idea down: the principal focus. Imagine a bunch of parallel light rays all flying straight at a curved mirror. The one single spot where they all meet up after they bounce off, yeah, that's the principal focus. It's like the mirror's natural gathering point for light. And that idea leads us straight to our very first tool. The distance from the mirror to that focus point is what we call the focal length, or F. And the rule couldn't be simpler. The focal length is just half of the mirror's radius of curvature, r, the radius of the big sphere that the mirror is a slice of. So our first formula is F equals r divided by 2. That's it. The curvier the mirror, the shorter the focal length. This is our foundation. Okay, so now we get the mirror's basic properties. But the big question is, if you put an object in front of it, where exactly is its reflection going to show up? For that, we need the main event, the mirror equation. And here it is. This is the absolute workhorse of optics. It's a beautiful little formula that connects three things: the focal length, F, the distance of the object from the mirror, U, and the distance of the image from the mirror, V. If you know two of these, you can always find the third. It lets you pinpoint the exact location of any reflection. Now here's the catch. To get this formula to work, you have to be super careful with your positive and negative signs. It's all part of a system called the Cartesian sign convention, and honestly, it's the secret to getting the right answer. So let's break it down. For V, the image distance, a positive number means you have a real image, one you could actually project on a screen. A negative V means it's a virtual image, like the one you see behind your bathroom mirror. For the focal length F, it's negative for concave mirrors that bring light together and positive for convex mirrors that spread it out. And U, the object distance, well, for a real object, it's pretty much always negative. Getting these signs right isn't just a suggestion, it's absolutely crucial. So we figured out where the image is, but that's only half the story, right? What does the reflection actually look like? Is it huge? Tiny? Is it even right side up? For all those questions, we have the magnification formula, M. It's just a simple ratio, negative V divided by U. But this little formula is awesome because it does double duty. It tells you about the image's size and whether it's been flipped over. So once you calculate M, how do you read the answer? It's really straightforward. If M is a positive number, your image is upright. If it's negative, the image is inverted or totally upside down. And the number itself? If the value is bigger than 1, the image is enlarged. If it's less than 1, the image is smaller. It's amazing. You get a complete description from just one little number. Okay, enough theory. Let's put our new toolkit to the test. Let's say we have an object and we place it 30 centimeters away from a concave mirror. We also know that mirror has a focal length of 20 centimeters. The question is, where's the image? First up, we grab the mirror equation, and we have to remember our sign conventions. It's a concave mirror, so the focal length F is negative 20 centimeters. The object is real, so its distance U is negative 30 centimeters. We just plug those values into our formula. After a little bit of algebra to solve for V, we get negative 60 centimeters. And that negative sign is the key. It tells us the image is real and it's located 60 centimeters in front of the mirror. So we know where it is, but what about its size and orientation? Let's say our original object was 5 centimeters tall. Now we use our magnification formula, M equals negative V over U. We just plug in the numbers we already have. V is negative 60 and U is negative 30. So that gives us a magnification of negative 2. So what does that mean? Well, the negative sign tells us the image is inverted, it's upside down, and the 2 tells us it's twice as big. So our little 5 centimeter object has turned into a 10 centimeter image, and it's completely flipped over. Now, here's where things get really cool. This entire toolkit we've just built for mirrors Well, you can use almost the exact same logic for lenses, which bend light instead of reflecting it. Just look at them side by side. The lens formula on the right is almost identical to the mirror formula. The only, and I mean only, difference is that the plus sign becomes a minus sign. Just think about that for a second. One tiny change, a plus to a minus, and our entire powerful system adapts from reflection to refraction. That is the elegance of physics right there. So now that we have all these tools, how do we tackle any problem they throw at us? Well, it's all about having a clear, simple strategy you can use every time. It really just boils down to a simple 3-step guide. First, figure out what you're working with, a concave mirror or a convex one. That'll tell you the sign of your focal length. Second, apply all your sign conventions for the stuff you already know, like the object distance. And third, just pick the right tool for the job. Need a location? Use the mirror equation. Need to describe the image? Use the magnification formula. Okay, let's do one last example from the real world. You know that mirror on the passenger side of your car? The one that says objects in mirror are closer than they appear? Let's find out why it says that. The math will tell us everything. Step 1. Gather the info. It's a convex mirror, so we know its focal length is going to be positive. The problem says the radius of curvature is 3 meters. Our formula is F equals R over 2, so the focal length is plus 1.5 meters. The bus is our object, so its distance, U, is minus 5 meters. Now we just plug it all into the mirror equation. We rearrange the formula and solve for V, and we get about plus 1.15 meters. Okay, so what is that positive sign telling us? Remember our rules? It means the image is formed behind the mirror. It's a virtual image. You can't project it onto a screen. And that's exactly what you'd expect from a car's rearview mirror. And for the final piece of the puzzle, let's check the magnification. We calculate M using negative V over U, and it comes out to positive 0.23. Let's decode that. The positive sign means the image is erect, it's upright, which is kind of important when you're driving. And because 0.23 is way less than 1, the image is diminished, or a lot smaller. And that is exactly why we use convex mirrors in cars. They shrink the image so you can see a much wider view of the road behind you. The math perfectly explains the design. It's pretty amazing, right? We've just seen how these basic formulas can perfectly explain something as common as a car mirror. But here's the thing, the exact same principles of focusing and magnifying light are just scaled way up in giant telescopes to create images of galaxies billions of light years away. It's the same math, the same toolkit. It just goes to show you how a few simple, elegant equations can unlock the secrets of our world, from the reflection in a spoon all the way to the very edge of the cosmos.